Dear ladies and gentlemen, my name is Benedikt Schmucker and I'm pleased to present the paper Implementation of an Intelligent System Architecture for Process Monitoring of Machine Tools during the CIRPe Online Conference 2020. The presentation is divided into 4 parts. After a short introduction, part 1, in which I present the motivation and objective of the collaborative work, I would like to present the implemented system technology and architecture in more detail under point 2. In the third section, I would like to present a cutting force reconstruction approach which uses motor currents of the feed drives as an input. The machine data can be acquired using the system technology which is introduced in section 2. In the end, I would like to summarize the presentation and give an outlook to future studies and research. Let's start with the introduction. Depending on the selected process parameters and the material being machined, high to very high cutting forces may occur during machining. On the one hand, these forces cause static deformation of the tool and the workpiece and a tracking error along the tool path. In addition, the acting loads also result in a dynamic vibration excitation of the tool workpiece combination. The vibration occurring during machining can be divided into 2 categories, force and self-excited vibrations. During machining, forced vibrations are mainly caused by the cutter workpiece engagement. Consequently, the teeth engagement also determines the frequency of these externally excited vibrations. This can also be seen in the left frequency spectrum. The amplitudes lie exclusively on the harmonics of the tooth's passing frequency. To avoid large form errors due to the forced vibrations, it should be ensured that the tooth engagement does not match resonance frequencies of the machine tool or the workpiece. The amplitude of these vibrations can therefore be reduced by a careful choice of process parameters. In industrial practice, the self-excited vibrations are mainly caused by the so-called regenerative effect. Hereby, the tooth cuts into an already wavy surface, which leads to a chip thickness modulation and thus to so-called chatter vibrations. Therefore, chatter vibrations do not match the harmonics of the tooth passing frequency. Rather, the vibrations usually occur in the vicinity of 1 or more natural frequencies. Self-excited vibrations cause high loads on tool, workpiece and drive components and must therefore be avoided during machining operations. In the following short video clip, you can see and hear the occurrence of chatter vibrations during an end milling operation. In the frequency spectrum, at the top left, you can see the chatter frequency, which does not correspond to a harmonic of the tooth pathing frequency. In addition, the chatter marks are clearly visible on the machined surface. There are 2 ways to prevent chatter during machining operations. Number 1 is to detect chatter and adapt the process parameters online. This is also known as process control. In recent years and decades, various approaches have been published for process parallel chatter detection and avoidance, which use either external sensor signals or machine data as an input. Major challenges for the process control are still the acquisition of high-frequency machine data and the adaptation of process parameters during the execution of the NC program. Section 2 presents a system architecture that enables these 2 tasks to be performed on an external device, on an edge computer. The second approach to prevent chatter vibrations is a systematic process parameter selection based on stability lobe diagrams. An exemplary stability lobe diagram is shown in the right figure. The critical cutting depth indicates up to which cutting depth the cutting process is assumed to be stable. To obtain such a diagram, various input variables must be determined. It is particularly important to know the dynamic behavior of the workpiece and the machine tool. To determine the dynamic behavior of the machine tool during operation, an operational modal analysis can be used. A classical experimental modal analysis is not suitable, because the machine tool controllers are not active and the spindle does not rotate. For such an operational modal analysis, cutting forces must be determined during machining and synchronized with the displacement measurements. How the cutting forces can be reconstructed based on motor currents is shown in section 3. The second part of the presentation will now introduce the system technology and architecture used for data acquisition, data processing, and process control. As presented in the introduction, the system technology must enable the high-frequency acquisition of machine data and external sensor data. The goal is to achieve a sampling frequency of 1 to 10 kHz for both data sources. This goal was achieved with a two-part data acquisition system. A back-off industrial PC enables the acquisition of external sensors such as accelerometers via a field bus coupler. The real-time environment of the back-off PC, which is known as TwinCut, captures the data from the bus coupler at a rate of 1 kHz. Through so-called oversampling inputs, the TwinCut cycle can be divided up to 50 times. The planned acquisition rate of 10 kHz can thus be reached. A similar approach was used to acquire the machine data. A compile cycle collects the internal data, such as motor currents or encoder data, directly on the CNC controller. From there, the data is buffered and sent as packages to the external devices. But it must be mentioned that the machine data interface implemented in this cooperation is specifically designed for Siemens control systems. As soon as the data from both data sources are available on the back-off PC, data analysis can be started. This does not necessarily have to take place in the TwinCut environment, but can also be executed in local or network applications. The automation device specification provided by Backoff is used for this purpose. Among others, MATLAB, Python, and C++ clients are available for the ADS communication. If a process monitoring system detects unwanted vibrations, both the feed rate and the spindle speed can be adjusted. For such a corrective action, the TwinCut environment sends two signals to the PLC. The trigger signal indicates that a particular process parameter must be changed. After setting this trigger signal, a special override becomes active, which sets the commanded values to the new actual feed rates or spindle speeds. In the illustrated example, only the spindle speed is changed. The feed rate remains at the commanded value. The communication between the TwinCut environment and the PLC was implemented using a commissioning adapter from the Enterprise IBH Softec. This adapter allows to write analog and digital inputs without adapting the PLC project. Synchronous actions ensure that the commanded values become active during the execution of the NC program. After the introduction of the system architecture, an exemplary application for this system technology, the cutting force reconstruction, will now be presented. Cutting force measurement during machining can be classified into direct and indirect measurement techniques. Direct methods are characterized by using dynamometers, spindle-integrated force sensors, or strain gauges close to a cutting region. The acquisition of motor currents for cutting force reconstruction is considered as an indirect approach. Since sensors close to the machining area are exposed to the harsh process environment with lubricants and metal chips, they tend to fail frequently, resulting in additional costs for maintenance and commissioning. However, the measured motor currents also contain frictional components and inertial loads of the rigid body motion, which need to be first separated out of the acquired current measurements. In addition, the structural dynamic transfer behavior from the cutting region to the feed drive motor must be considered. To be more precise, the shown transfer characteristics from the tool via various mechanical components and couplings to the feed motors must be determined. Otherwise, no dynamic forces can be measured. For identifying frictional and inertial loads and for building the dimension transfer function, the experimental setup depicted in the two right figures was used. A Kistler dynamometer was mounted on the machine table of a Grob G352T. By carrying out air cuts and actual slotting tests, the inertia and friction influences were identified. Thus, the actual feed drive motor current, which is caused by the chip removal process, could be quantified. Measurements of the actual cutting forces from the dynamometer and the simultaneously acquired motor currents at a tooth-padding frequency of 70 Hz up to 130 Hz were carried out. Hence, the transfer function between motor currents and cutting forces, which is valid for this process parameter range, could be determined. As the two frequency spectra on the bottom left show, excitation by the test up to 500 Hz can be observed in the dynamometer measurement and in the motor current traces. It can therefore be assumed that the calculated transfer function enables the reconstruction of the cutting forces up to 500 Hz. Additionally, Iglesias et al. Showed that the determination of the transfer function can be improved through a continuous increase of spindle speed and by varying the cutter workpiece engagement conditions. Because discrete excitation peaks, as seen here and here, are avoided and a richer excitation spectrum follows. These two assumptions will be evaluated in future studies. However, as the figure on the right shows, cutting forces could be reconstructed based on a locked motor currents. In the moving axis, the x-axis in our test setup, the reconstruction of the cutting forces already worked well, and a good agreement between reconstructed and measured forces could be observed. In contrast, the reconstructed forces in the stopped axis showed greater deviations due to larger influence of friction, and the reconstruction for the stopped axis, in our example the y and the z axis, must be further improved. I would like to proceed with the summary of the presentation and the outlook to future studies. The structure of a system technology which enables the acquisition of high-frequency machine data and external sensor data was shown. This data can be analyzed by local or network applications with the help of the ADS communication. An exemplary application which processes the acquired data is the presented cutting force reconstruction. For the reconstruction of cutting forces, the transfer behavior from the tool to the feed drive motors must be known. This transfer function was determined using slotting tests and air cuts. For the moving axis, the cutting force reconstruction already worked well, but for the stopped axis, further research is necessary. Aslan, Yamada, and Sato already showed interesting approaches here. It is also necessary to assess whether other engagement conditions, for example half or quarter immersion cuts, and other experimental strategies such as increasing spindle speeds, improve the determination of the transfer function. However, the system technology cannot only be used for cutting force reconstruction, but further process monitoring, process control, and process optimization tasks can be implemented based on a presented system architecture. With a warm thank you to the German Federal Ministry of Education and Research for the funding of our research project with the title Closed Loop Manufacturing 4.0, I would like to end my presentation, and I'm looking forward to an interesting discussion.